question. Okay? Question. I got a circle. Other than right here and right here, can you easily find a tangent line everywhere on the circle? That's not really, a complicated thing. If I said, how about right here? We all agree the tangent line would look something like, like this. Okay. I would like to find the slope of the tangent line. I said other than the two verticals, because those would be undefined. Does that make sense? Is this just a simple derivative problem? Because the derivative is how we can find the slope of the tangent line. Is this a simple derivative problem? There's something not right. What don't you like? All the derivatives you've taken so far were y equals a function of something, right? What's wrong with this one?
There were both on the same side.
Well, first, is that a function? Yes or no?
Mm-hmm.
It's a circle, so one x value usually has
Two values.
more than one y. That's not good, is it? By the way, would you agree a circle is an important shape?
Yeah.
Yeah, one of the most important shapes. But a circle is not a function. A circle doesn't like calculus. Things that are not functions are not very friendly in calculus, but I would like to find the slope of the tangent line. But it's not a function. If I can write y equals, then it's a function. But I cannot isolate the y, can I? Because there'd be a plus or minus. Oh gosh. So we're going to start with this. So what if I thought of this as top half, bottom half? The top half I could write as y equals r squared minus x squared, square root, I'll write it to the 1/2. And the bottom half would look like what?
Minus?
Yeah. Now, are those functions?
Yeah.
There's an old trick. If I wanted to graph a circle on my graphing calculator, it's not possible to graph a circle on a graphing calculator. But I want to graph my circle on my graphing calculator, so what do? I do that. I do top half, bottom half. Can I graph two functions on my calculator at one time?
Yep.
Sure. So that's what you'd actually do. You go, oh, okay, do the top half, do the bottom half, and now I see a circle on my screen. So I want to take derivatives this way, top half, bottom half. So now we're going to apply our chain rule that we learned last day. So dy dx, now it's thing to the 1/2 power. So what's the derivative? Thing to the negative 1/2. But I still have to take the derivative of the inside. That's called the chain rule factor. R is a constant. R is the radius of the circle. R is not a variable.
Negative 2x.
Beautiful. Are we all cool with that? This is the derivative of that circle. Now, can I, or I should say this half circle, the top half, can I simplify that?
Yeah.
Well, it certainly cancel the 2's. So how about if I write it like this? Negative x over, is that correct?
Yeah.
I just put the root back. If y equals the square root of r squared minus, then isn't this just the same as negative x over y? Is that the same thing?
Yeah.
Now I did something really weird. I have a y in the answer, but I don't have a function. Maybe that's okay. So we just said at every point on the top half of the circle, the slope should be negative x over y. Well, let's see if that makes sense. Well, how about right here? What should the slope be? Right there. That should be 0. What's the x-coordinate right there? Isn't it 0?
Yeah.
Oh, okay. How about in general, in the first quadrant, aren't all my slopes negative? In the first quadrant, both x and y are positive, aren't they? And that would be negative. Oh, okay, that makes sense. How about in the second quadrant? Aren't all my slopes positive? But x is negative and y is positive, so that again, that works, doesn't it? And what about here? Well, the slope would be undefined because I'm dividing by 0. And okay, that seems like that'll work. Not the fastest, not the most efficient route, but it definitely works. All right. Let's do the same thing for the bottom half. Well, everything should look exactly the same as what I just did, except that I have this negative sign.
So it's the positive version.
So I'm gonna have negative. I mean, you already know what the final answer is gonna be, because it's just gonna be the opposite sign of this. And so that's gonna be, I have two negatives here. I'm gonna go kind of crazy. I'm gonna write it like this. In fact, I'm gonna go, oh, sorry, negative. We know this is correct. Is this correct?
No,
I'm waiting for-
you could simplify that as just positive.
Yes, I can, but is it correct?
Oh,
I want to write it like this because my numerator now looks exactly the same. Oh, and by the way, look at my denominator. Isn't my denominator still exactly y?
yeah.
Oh, that's why I did that. This is kind of cool. We just differentiated the top half and the bottom half as separate entities, and we got the same answer, didn't we? At every point on the circle, the slope of the tangent line is negative x over y. Now, what I did was absolutely correct mathematically. Not necessarily the most efficient route. So we're gonna come back to this one in a bit, and I'm gonna show you an alternate way of doing this that's way, way faster.
Can you repeat what you said, the slope of the tangent?
At every point on the circle, the slope of the tangent line is gonna be exactly the negative of x over y. How do I know? Because we just figured it out. By the way, this is kind of interesting. Did the r figure into this at all?
No.
No, didn't matter how big the circle was. It only mattered what point on the circle you were. That seems kind of cool. Okay, so let's do this. I'm gonna write it over here. M of the tangent is negative x over y. We all agree. I need the board space now, so I'm gonna erase this stuff here. So I'm gonna give you a new problem now. I'm going to tell you that f of x cubed plus 4x squared times f of x equals, how about x to the fourth power. I want to find f prime of x. Now it's kind of goofy notation. That's pretty ugly. Do you think it's possible for me to manipulate that and isolate the f of x and write f of x equals? Probably not. In fact, if I just said randomly make up, just make up something, I might not be able to isolate the function. I could not isolate the y here. We had to do this as two different things. But I still want f prime of x. So here's what we're going to do. We're going to differentiate both sides. If two quantities are equal, then their derivatives have to be equal. It's a fairly simple thing. I have two curves that are the same. Their derivatives have to be the same. So let's differentiate both sides. That means I'm going to do this. To both sides. And the results I get, I will be able to get the f prime of x all by itself. Okay? So, I'm differentiating thing cubed. I'm differentiating thing cubed. What should I get? 3 thing squared times derivative of thing. What's the derivative of f of x? F prime of x. Oh, okay. That wasn't that bad. Next, I have a product of 4x squared and f of x. I have to use the product rule here. So, product rule says it's first times the derivative of the second. What's that going to be?
F prime x.
Yeah, I like that one. That one's pretty easy. Plus the second times the derivative of the first, which would be
8x.
8x. That's the left side. Right side, I think that's pretty easy. What's the right side?
4x cubed.
4x cubed. I am finished taking derivatives. The instruction was to find f prime of x. But hopefully you notice I have an f prime there and I have an f prime here. Do you think I could gather terms and factor that out?
Yes.
Yeah, it turns out that's not going to be that hard. So these two terms have an f prime, this one doesn't, so I'm going to send this one packing. So I'm going to send that guy to the other side. I don't want him over here. So on the left side, I have 3 times f of x quantity squared plus 4x squared all times f prime of x, correct? That's what I have on the left side. What will I have on the right side? I'll have 4x cubed minus, how about 8x f of x? Because I'm subtracting that from both sides. Can I write f prime now? Question. I have something times f prime equals something else. Can I just write f prime now as the quotient? What's left? So f prime should be this quantity over this quantity. Did we do it? Yes, we did. It wasn't a trivial thing, but we were able to do it. We were able to do it without actually isolating the f of x in the first step because we couldn't isolate it. Just like in the circle, we couldn't isolate it. And notice that my final answer, the derivative, has f of x's in it. That actually should be expected in this kind of scenario. Question? We're going to keep going. Okay? This is what is called implicit differentiation. And what this means really is something like this. If I said y equals the sine of x, y is explicitly defined as a function of x. There's no ambiguity here whatsoever. But when I wrote x squared plus y squared equals r squared, you can't isolate the y. So we're really thinking of, I'm treating y as a function of x because I want to write slopes of tangent lines, but I cannot explicitly solve for the y. So it is implicitly defined as a function of x. If I can't isolate the dependent variable, which in this case is the y, in this case it's the f of x, then I differentiate it this way. Okay? So this is called implicit differentiation. This is my result. This is the only way I can get this. It's not the worst thing in the world. Okay? It's different. It's very different. And this is, people don't always love this because it's a little bit confusing at first. So let's do a totally different problem now. Let's do, I have y cubed plus 4x squared y, and I want that to equal x to the 4th, and I want to find dy dx. And just like the circle, I cannot explicitly isolate the y. So what we're going to do is, just like before, we're going to differentiate both sides of this with respect to x. I'm giving you the instructions. So on the left side, I'm differentiating all of that. On the right side, I'm just differentiating that. Now, when I differentiate y cubed, think of y as function of x. Don't think of y as variable, because I'm not differentiating with respect to y, I'm differentiating with respect to x. Only when you differentiate with respect to the same variable do you treat it as a variable. So if I said, and we get really sloppy, on the right side, I want you to differentiate x to the 4th. You know it's 4x cubed. It's implied that I'm differentiating with respect to x. But if I meant to differentiate with respect to a different variable, I'd have to say that, and that would give me a very different answer. I'm differentiating everything with respect to x. This is not an x, so I can't treat it as an x. I have to treat it like function. So this will be what? 3y squared times the derivative of y, which is dy dx. If I just wrote 3y squared, that would be incorrect, and I wouldn't be able to finish the problem. These are not the same variable. They don't have to be.
Why didn't we do that with R?
Well, I haven't shown you that yet.
Okay.
When I said we're gonna come back to it and do it a more efficient way,
Okay.
we're gonna do this on that problem in a moment, you're gonna like it.
Okay.
Because you saw how much work that was. So that's called the brute force way, the way we did it. Everything was accurate, everything was correct, but it took us a long time. And we even had to employ a little bit of cleverness. Okay? Product, think of this as x and function of x. So first times derivative of second plus second times derivative of first. Now I'm done with the left side. And what's the derivative of the right side?
Oh,
4x cubed.
yeah.
Okay, I'm done with the calculus. I wanted to write dy dx equals. I have two different terms with the dy dx. dy dx is not being raised to a power, so I can factor it out. So how about if I rewrite this as 3y squared plus 4x squared all times dy dx? And then that equals, and I'll throw that one over there like I said. So finally, when all is said and done, this is not the simplest thing at first, but all I'm doing is taking some derivatives and, this is the answer using implicit differentiation. Now, does anybody notice anything about the two questions I just did?
It's the same thing, just,
They're the exact same problem. Yeah. I just did the exact same problem twice. Everybody in this room probably felt more comfortable with the f of x because there's just no ambiguity. I have x and I have f of x and they're different animals altogether. And we did this from beginning to end. So why did I do this? Because you're never going to see the problem written this way. You're only going to see it written that way. In other words, you're always going to see it with x's and y's, not x's and f of x's. But what allowed us to do this one easily? When you look at y, think f of x.
you wrote on the second to last line, you
Did
wrote
I?
x squared, and then you rewrote it as squared, but it's cubed.
Oh, that's because thank you. I can't read my own writing there. That's a third, right? Are these answers exactly the same? Yeah, because y and f of x are the same thing. So when you're doing implicit differentiation, here's the thing. Do not rewrite the problem. But when you see y, see f of x. So its derivative is not 1, it's dy dx. Because when you differentiate f of x, its derivative you would tell me is f prime of x, right? You wouldn't say it's 1. So this is how you do implicit. So let's go back to this one then. Could I have done this one implicitly right from the beginning? Yes. There's our answer up there. I want to, like we did before, differentiate both sides with respect to x. Because we are implicitly defining y as a function of x. I cannot explicitly do it because I can't isolate the y. It turns out there's a great many problems that are out there where you cannot isolate the dependent variable, which in this case is y, but you can still take derivatives. So when I differentiate the left side, what am I going to get?
2x, 2y dy dx.
Good. Because the derivative of y is not 1. It's dy dx. Now when I differentiate the right side, what am I going to get?
2r.
R is a constant. R is the radius of the circle. It's not a variable.
0?
0. Good. When I differentiate the radius, I'm just going to get 0. There's no variable on the right side. If it helps you put in a number there. Huh. I think isolating the dy dx won't be that bad. Yes? No? Maybe?
I'm kind of lost why the r squared is equal to 0.
R is the radius of the circle.
Yes.
It's not a variable.
Okay.
It's a number.
Okay.
I don't want to put in a number because then this statement would only be true for that one value. I'm saying no. All circles have a radius. The radius is a number. X and Y are variables. The radius is not. So when I differentiate r squared, I get 0 because I'm differentiating the square of a number, not the square of a variable. Does that help?
Yeah.
Now, I'm almost done.
So 2y to the other side.
wouldn't this be then, oh my goose, that was so much easier, wasn't it? Would you agree that was a lot easier?
Yes.
Yeah, it's way easier. Implicit differentiation is not everybody's favorite at first because it's a little bit more complicated. I gotta be paying attention a little more. But it gives me the answers. And here's the crazy thing. The thing I'm looking at does not have to be a function. Heck, I could take a figure 8. That's a totally evil shape, that's cool. And I could talk about the slope of the tangent line at every point on that figure 8. But I'm not gonna be able to write y equals because it's not a function. Right? Ellipses are not functions. Hyperbolas are not functions, but I can still ask for derivatives. The hardest problem that we generally run into in terms of derivatives is the second derivative implicitly. I tend to stay away from that one because algebraically it can be really, really nasty in general. Second derivative of a function in general is not bad. If y is a function of x, finding 2 derivatives usually is not too terrible. Implicitly, it can be really awful. But I want to do it for the circle because this is probably the friendliest one you're ever going to see. So I would like to find the second derivative. And again, the second derivative probably involves both x and y in the answer. So we agree then the first derivative, this is the slope of the tangent line at every point on my circle is just going to be this quotient. And when I'm here, when I'm on the x-axis, I have 2 vertical tangents there, and those are the only places where this would be undefined, which seems consistent. I would now like the second derivative. So the second derivative, which is written this way, is the first derivative of the first derivative. So it's redundant here, write it all out. There, I'm going to differentiate this. Any ideas? Quotient rule. Yeah. My denominator is not a quantity being raised to a power, so I mentioned last time that if your denominator is something being raised to a power, using product rule is going to be easier. But my denominator is not being raised to a power, so product rule isn't going to save me any time. So I'll just go straight up quotient rule here. So if I do quotient rule, I'll get, now, what do you want to do with that negative? Do you want to leave it in front of the quotient? Do you want to apply it to the x, apply it to the y, or would you like to move it completely outside the derivative?
Outside.
All are correct. I like moving it outside. So in other words, kind of like this. A lot of us, this will give us trouble. We don't know what to do with it as we're taking derivatives. So how about I just, it's a constant, right? It's -1 times. So I'm going to put it on the outside. Now, O d high, what's the derivative of the top?
1.
Mine is high d ho over ho. Well, that was easy. Except my second derivative has the first derivative in the answer. So, anybody got an idea of what you think might be a really good idea?
Replace it with -x over 1.
Exactly. Just substitute that in. So now I've got the negative of y minus x times -x over y. Almost there, but I have a quotient in my numerator. I don't like quotients in my numerator. What's the easiest fix? What's the easiest fix?
Y over Y.
Multiply top and bottom by y. Y over y. Beautiful. Is that legal? Yeah. But that gets rid of the quotient on both top and bottom, doesn't it? Or individual quotients, I should say. So now I've got what? Y squared
Minus, plus x.
plus x squared all over.
Y cubed.
All right. That's a great answer. It's a really great answer, but there might be a greater answer. What does x squared plus y squared equal?
1.
No.
Oh, R squared.
Doesn't x squared plus y squared equal r squared?
Oh.
Oh, could I just then make this that? Cool. That's what it is. That's the best answer I can give because it's the simplest answer I can give. If I left it like this, that's not wrong, but x squared plus y squared is equal to r squared. That's how we started the problem. So implicit differentiation, it's a bit of a game. It's a bit of a puzzle. And it is not a trivial thing to do, but it is something that we're going to use often. Here's the main reason we use it. Right now, we have developed a number of derivative formulas where we had to use the definition of the derivative. There's no other way. But after we developed sine and cosine, we did not use the limit version to get tangent. We used quotient rule, didn't we? So it turns out when we develop things like our all of our trig functions, which we have, and exponential functions, we're going to use implicit differentiation to get their inverses, like the logarithms and the inverse trigs. It turns out it's way, way, way more efficient and way simpler than limits. So we're going to actually have a second way of finding a lot of our derivative formulas by using implicit differentiation. And that's going to start actually pretty soon, like next class. Okay, so let's continue practicing this. All right. I've got the sine of xy, and I want that to equal about x squared. I want to find dy dx. Well, the only y in the problem is inside the argument of sine. I'm pretty sure I can't get that by itself. Okay? So what? Differentiate implicitly. I'm going to take the derivative of both sides. And I always write it out, so I'm leaving my instructions. This is what I'm actually going to do. Derivative of the left side equals derivative of the right side. But the nice thing is when I differentiate the left side, dy dx is going to show up as a chain rule factor. It's going to be a multiplier, which is why I'll be able to factor it out. I'm not going to try to get the y by itself. I want to get the dy dx by itself, because that's the thing I'm actually looking for. All right, I want you to differentiate the sine of thing. What are you going to get? The cosine of thing. But times what? I'll write it out. Times the derivative of thing. Ooh. What I have is correct. I'm not done yet. I have to differentiate x times y. How am I going to do that? Product rule.
Yeah.
Yeah, product rule. Straight up.
I have a question. Why are we differentiating xy?
Why are we differentiating?
xy.
Because it's not just an x. It's the chain rule factor.
Oh, right. Okay, sorry.
Yeah.
My bad.
But no, it's the right question to ask, because if I don't, two problems. If I don't do it, I'm never going to have a dy dx in the answer.
Right.
Well, that would feel below average, wouldn't it? What is this derivative? It's product rule. So it's first
Times dy dx plus y.
plus second times, I'm going to write it times. I know it's redundant to write times 1, but I want to remind myself that I actually remember to take the derivative. Okay? That's the left side. What's the right side?
2x.
All this is 2x. I can't quite get the dy dx by itself yet. It would probably be wise for me to distribute first. Then the dy dx will be a standalone term. Okay? So on the left side, again, highway, you can see it. I'll put the x in front, it reads better. I'd have x cos xy times dy dx plus y times the cosine of xy. And what does all that equal?
2x.
It all equals 2x. Now, we're done with the calculus in the previous step. Can I finish this fairly quickly now?
Yeah.
That's the only term that has a dy dx, so I want this on the other side. So again, I was just remind myself, I'm going to send it packing. Sometimes I have to send more than one thing packing. I'm going to physically write it out. I don't want to skip steps or do multiple steps in my head. I might make a mistake. A lot of you can do a lot of the steps in your head easily, and that's not even an issue. It's arithmetic and stuff. The problem with doing some of the bigger steps in your head It's not that you're gonna do them incorrectly, but it means if you did do them incorrectly, it's impossible to locate your error. I teach the highest levels of mathematics, and I tell people, always leave an instruction manual of what you just did. Because when you're taking many, many steps to do a problem, you might have a 10 or 12 step problem, that's not unusual, and you get all the way to the end and it doesn't work. Then you can go back and say, okay, oh, here's my error. I can find it, and then I have to fix it from that point on. When you do steps in your head or skip steps, it's not possible to find the error. So you have one recourse in every problem, and that is to start from the beginning and doing the entire thing from beginning to end. It actually isn't saving you time when you're skipping steps, unless you're perfect. So whenever you have an error, you won't be able to catch it because you didn't write it down. There's nothing to fix. You won't be able to know where it went wrong. So it's always a good idea to show, that's an obvious step, but I might mess up the sign here. Now, the last thing I'm going to do is write this as a quotient. So far, so good? Yes, no, maybe?
Yep.
Everything I said is true, everything I said is correct. Is it necessarily the simplest answer? I mentioned this last day. When you have a trig function in the denominator, you shouldn't have a trig function in the denominator because the reciprocal of all trig functions is another trig function. Right now I have a trig function in numerator and denominator. Can we write this with only one trig function? Yeah. What's the reciprocal of the cosine?
Here's one.
The reciprocal of the cosine.
I see.
Secant. You're thinking derivative. Sorry. Right universe, wrong planet. How about if I did this? By the way, I'm not saying what if we did this. This is actually what you have to do to finish the problem. We have no errors, but we have a better version of the answer. So if I distribute this into my numerator, what happens when I multiply the cosine and the secant together? Yeah, I get 1. Oh, so I'm going to get 2x times the secant of xy minus y. All over
1. Wait.
X.
x.
Right.
Well, that's a bit simpler. Everything we said is true, everything we said is correct. And I gave you another tidbit last week when it talked about simplification. Remember what I said when you have stuff in your numerator but you only have one term in your denominator? What is often a good idea? When I say often, what I'm really saying is always, but we're still training ourselves.
Just pull it out.
Can you do better still? Yes.
2 secant xy minus y over x.
And I do think that is by far the simplest answer.
You have to switch the y and the x.
Did I? Oh, thank you.
Yeah.
What did you say? Y over x.
Yeah.
Thank you. Sticking sideways. This was our first answer. There's nothing wrong with it. We can just improve upon it. Wow, that's the only quotient I have left. I like that one best because now if I have to use this further to do other stuff, oh heck, what if I had to take the derivative of this? Yikes. This would be a lot easier to take the derivative of than this one. You agree? Yeah, it'd be way simpler. So implicit differentiation, when do you use it? When you cannot isolate the dependent variable. And right now we're only using x's and y's. That's not going to be the case forever. But right now I want to get you conditioned to doing things a certain way. If we start using multiple variables in every problem, it's just going to lend for confusion. That time is coming. All right, that we can have multiple variables in the same problem, like the second half of class today. But for right now, if I keep making y as a function of x, then my answers are always of the form dy dx equals and so on. But then I also know how to exactly apply my derivative rules. Implicit differentiation means I had x's and y's, but I could not start by writing y equals. I could not isolate. I could not get the y by itself. So I just kept going. But it also means that my final answer, my derivative, is likely to have x's and y's both in it. You see? And that's not a problem. But now when I want to find, if I said I want to find the slope of the tangent line at any given point, it would now be much easier to do that. Okay? Does that make sense? Why would it be much easier to do that? Because now I can give you the ordered pair. All right, let's keep going. All right, how about, let's do, I have x squared times the tangent of y minus 3xy squared equals 1. And again, our goal is to find dy dx. I have no idea what this looks like. I imagine it's something crazy wild and loopy all over the place. I want to find the slope of the tangent line at every point on this graph. And now we can do that. Okay, so I want you to start this on your own. I'm going to wait for you. And you're going to tell me what the first couple steps look like. All right, so far I've started each problem by physically writing d dx on both sides. Can I just start by writing the derivatives?
Yeah.
Yeah. When you're first learning something, you want to write everything out so you don't skip steps, so you don't get lost. You've done 5, 6, 12, 15, 100 problems. I'm taking the derivative of both sides. Can I just write the derivative of both sides as the next step? Sure. You notice I'm putting the d dx on the original question. I'm not rewriting the problem. So if I said, I want you to differentiate the left side, what are you going to have? It's a product.
X
so
squared times secant squared y times dy
the
dx.
secant squared of y, and then times the derivative of y because it's not an x. Times dy dx, good. Plus,
Tan y times 2x.
good. Tan y times 2x. That's the left side. Oh, I'm sorry, not equals. Sorry, we're not done. We have that turned out.
Oh,
Negative 3 times x times 2y times dy dx
Oh, you guys are on a roll.
plus y squared times 1. That's the whole thing times 3.
Plus y squared? That minus is throwing us.
Yeah, should we keep that out with the parentheses?
So, by the way, it's not plus. It would be minus again, but right now, would you agree that minus is kind of getting in our way?
Yeah.
So why don't I think of it like this?
Mm.
Now I'll put a plus sign. And now you see why, oh, it really isn't a plus. Because I'm subtracting the whole product rule, aren't I? So in the end, am I going to be distributing that negative? Yeah. Negative signs when you're doing product rule in general always get in the way because you're not always sure where to apply it. Well, actually, everything gets the negative sign. And what's the right side?
0.
All righty, well, I like that. So I want to go ahead and distribute the negatives. So I'm going to go like this. Are we good?
Yeah.
I just went ahead and distributed.
Yeah.
I do not like rewriting. This is one of my pet peeves. I don't like rewriting something unless I'm going forward, unless I'm actually doing the steps. To rewrite this entire thing just to distribute the negative, Now, when you're rewriting it, what are you going to do with the coefficients? When you're moving things around? Well, right, you got to put the coefficients back in front. Nothing should read 3 times x times 2 times y. That should read 6 times x times y. Right? So when we're now doing stuff, go ahead and move those coefficients. So what's moving, what's staying? These guys are going to stay. Those guys I'm sending packing. Because I only have 2 dy dx terms and they're both already on the same side. So when I rewrite this, I'm going to write it in a factored form. I've got x squared times the square of the secant function. What's this?
6x, negative 6x.
Minus 6xy all times dy dx. Now, everything else went to the other side, so this became negative and this became positive. So I think I might want to write that one first. And then what would this be?
2x.
Do you have to put the x in front?
You should,
You should. Why?
because it reads better.
If I wrote, is there anything wrong with this? Because that's exactly what you have. You put the 2 in front, you have tangent y times x. But what's the problem when you look at that?
It looks like 10y.
Is it tan of yx or is it tangent of y all times x? The answer is it's not really clear.
Linear dash.
So putting the x in front eliminates even the possibility of misinterpreting. Do people misinterpret their own writing sometimes?
Yes.
Yeah, because I write something sort of ambiguous, and then the next step, I read it for what I wrote, not for what I meant. And so by putting the variable in front, there's just no way to misinterpret. Okay, I'm almost done. This is the only thing left, is that guy right there. So when all is said and done, dy dx equals this
Divided by that.
over this. Is there any common factor top and bottom?
Y.
That's kind of ugly, that's an x squared. Can I factor anything out of the numerator? Yes? No? Not sure? I have two terms, there's nothing. Can I factor anything out of the denominator? X. Therefore, should I factor the denominator? Actually, yes, you should. Why? Because I need to know when my derivative is 0, but because I have a quotient, I'd also like to know where my derivative is undefined. Ooh. Meaning I can't have x. So writing this like this, x secant squared y minus 6y, is actually an improvement. Because we said last week, remember, whenever possible, write your derivative in a factored form. That would be a factored form. Now, have we had factored forms earlier that we could have considered? Yes. The denominator can't be factored, but do we have common factors on top in this problem? I have 4x cubed, I have 8x. Is there anything in common there?
Correct.
Yeah, here's where I would pull the 4, because I'm already pulling the x out. Now I'd have x squared minus 2y. So this would be a better answer. A lot of folks would rather write that in reverse order. Does it make any difference what order I add these?
No.
No. In baby algebra, you were told you had to put the x first, because that's descending order. Yeah, that's true, but that's really only if you're going to do long division or something like that. In this case, it won't matter. This is a better answer because now I can set each of my factors individually equal to 0 if I had to. And you will have to at some point. So again, if you can write your final answer in a factored form, we consider that the best answer. It's not wrong before, it's just not quite finished. I can go a step further. All right? We good so far? Now, are we still taking all the same derivatives we've already done? Yeah. This just looks a little bit different now. All right? Oops. How about we have the square root of x squared plus y squared equals, I don't know, how about the cosine of y cubed? That looks just terrible. It's a big yikes. So far we have, think of x to a power and then all 6 trig functions of x. We have product rule, quotient rule, and now a chain rule. But if it's not just a function of x, but a function of something else, we know how to apply all of those same rules. That's what the chain rule told us last day. Do you want to rewrite anything before you start?
The root.
Probably the root would be wise. So how do I rewrite this?
But
Yeah, by the way, is it simply this? Is that correct?
No.
I'm winking out with my left eye, so you know something's up. No. The root of a sum is not the sum of the roots. Do calculus people sometimes do that? Oh, yes. I've already seen that multiple times. No, I can't do that. There is no math that allows me to do that. So how do I rewrite it then?
X squared plus y squared to the power of a half.
Yeah, because when I differentiate, I'd rather have an exponent there. It's a little easier to interpret. I can differentiate with a root, but I might not get it right. And then the derivative looks even weirder, doesn't it? I don't know what exponent to put. So now when I differentiate both sides, I'm going to go back and write it again. I have not just thing, I got stuff raised to the 1/2 power. So what's the derivative?
Half times x squared plus y squared to the power of negative a half plus.
Now this is tricky.
Times.
Now my chain rule factor is the derivative of the inside, the whole inside. So what's the derivative of the inside?
2x
2x,
2x
that was easy.
plus
2y dy dx.
Finally I get a dy dx. That is the complete derivative of the left side. Now the right side?
sine y cubed.
Negative sine.
Negative sine, sorry.
Almost there. Negative sine of y cubed.
Times 3y times dy dx. 3y squared. Sorry.
And then dy, oh boy, this one is very deep. Are we done with the calculus? Is there any more calculus to perform?
No.
No. The rest is algebra. The problems that we did last day when you had, quantities to powers times quantities to powers and it got really involved, if you remember, you were done with the calculus really early. The whole rest of the problem was factoring and, gathering terms. Now it's kind of the same thing. Every term that has a dy dx in it, I need. But this is kind of yucky. There's a lot of things I can do. I don't like that negative 1/2 power. That feels like it's in the way to some degree, and it might be. But let's go ahead and, but by the way, I have a 1/2 and I have a couple of 2's. Can I deal with that? Can I take this 1/2 and do this?
Yeah.
Yeah, I can't multiply it into the root, but I can distribute it into here. And that might help a little bit. Okay, so now what have I got? I've got x squared plus y squared to the negative 1/2 times x plus x squared plus y squared to the negative 1/2 times y times dy dx. And on the right side, I have negative 3y squared times the sine of y cubed times dy dx. Okay? Something's got to move. What do you want to move? I either am going to move this to the left side and this to the right side, or just this to the right side. Does it matter which way I go? No, what's the least amount of work then? Moving 2 terms or 1 term? What's the least amount of work? Picking up 2 heavy objects or 1 heavy object? Let's see. I think moving 1 term is less work than moving 2 terms, so I think I'm going to move that guy. So the left side is now x. Oh, I'll leave it in that form for. I'll write it like this. And on the right side, both terms are negative. That's not a problem because I'm going to be factoring in the end. So on the right side, what do I have? I have negative 3y squared times the sine of y cubed minus this all times dy dx. So far, so good? So it appears that dy dx is going to be a big old gruesome quotient here. And whether you write it as to the 1/2 power or you write it as a square root, it really doesn't matter. It's not going to change anything in the long run. Now, everything I've said is true, everything I said is correct. Is that the best final answer I can give? Why not?
You have two quotients in your.
I still have quotients within my quotient. Now, there's multiple places in this problem, by the way. There are multiple places you could have dealt with this, and it wouldn't have changed anything. I could have way back here said, let's just multiply both sides by the positive root to get rid of it. I could have said, let's just multiply both sides by the root to get rid of it. But now I have to multiply top and bottom by the root to get rid of it, don't I? So I'm going to now multiply top and bottom by this. Then I will no longer have any quotients within the quotient. Okay? So what do I have on top now?
X.
And that's it. Oh, okay, I like that.
And
Now, this and all this go together. That's a busy term. So negative 3y squared sine of y cubed. And if you want to write that as a square root, that's fine. Because the original problem, it was a square root. I think at this point, maybe I do write it as a square root. Okay. Minus what?
Y.
That's it. Ooh, that looks less horrific now, doesn't it? Still looks terrible, but it's a lot less terrible. Of the degrees of terrible-tude, this is a much lower level than it seemed a moment ago. So you're getting your feet wet here with implicit differentiation. This is how you do it. So I have a problem where I cannot isolate the dependent variable, which right now is the y. So I differentiate both sides of the equation. I create the dy dx terms because they're going to be chain rule factors. I isolate those, I write my answer. And in every case so far, you've seen the answer ends up being a quotient. Yet that's going to be the common thing, because you're going to end up with dy dx times a quantity equaling another quantity. And that's why your final answer is always going to look like a quotient. Okay? Questions? All right, let's go ahead and stop recording there. All right, the next thing we're going to do is actually one of the very first applications. Make sure I've got it written down correctly. One of the very first applications that we do in calculus, and it's one of these ones that I would hope would make perfect sense. So here's the thing. How many have ever been like out in the lake and you've got like the rope swing, you know, and you land out in the lake? You guys know what I'm talking about? You know, so imagine you're hovering over a spot in the lake. You've got the rope, but that tree branch goes way, 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 way out there. So you're not right next to the shore. And you're hovering over the lake and you decide to just, I don't know, just drop a pebble. What are you going to see? Is this what you're going to see? You're going to see ripples. Do the ripples speed up? Do they slow down? Do they move at a constant rate? They will move at a constant rate until when?
Sure.
Well, the end. Until they reach the end of the world. Until they reach an object. Could be the shore, a boat. Right, until they make contact with something. But they will move, and they will move at a constant rate. Do you agree? There's no question they'll move at a constant rate. So what about, I'm really curious about the area of each of these circles. Now, let's keep it really simple. Let's say every second. Let's say every single second the radius is increasing, we'll keep it really simple, by 1 inch. So when I haven't started yet, there's no radius. And then 1 second, and at 2 seconds, and then 3 seconds, we'll keep it really, really simple, okay? Well, then that would be, and then pi r squared, and pi r squared, and then pi r squared, and pi r squared. My radius is growing at a constant rate. It's growing at one inch per second. But is my area growing at a constant rate?
No.
No, definitely it's not growing at a constant rate. It's getting bigger faster, isn't it? Huh. What if I wanted to know how fast my area was growing at any particular time? I want the instantaneous rate of change of how fast my area is growing. If you're driving along a freeway and you're changing speeds, you don't find your instantaneous rate of change by taking a period of time and saying how far did I travel divided by the time it took me to travel. That would be your average rate of change. That would be the slope of a secant line on a curve. But if you wanted the instantaneous rate of change, we know that's the slope of the tangent line. I would like the instantaneous rate of change of the area at any given time, because clearly it's not changing at a constant rate. It grew 1 pi, it grew 3 pi, then 5 pi, then so on and so on and so on. Well, that presents an interesting problem, but I think it involves derivatives, don't you? I want the instantaneous rate of change. Well, what is the area of a circle?
Pi r squared.
Pi r squared. So obviously I want the derivative of the area. So I'll call it dA dr. And that would be 2 times pi times r. Area is squared units, length units. Radius is length units. So this would be area per length. So this would still be length units, wouldn't it? Agreed? But I said per time. Isn't time involved here? Every second something's changing. Shouldn't time be somehow in this problem?
I mean, 2 pi technically is time.
No. And 2 pi is a measurement. It's the.
I mean,
In this case, it's a unit. It refers to the angle, but yeah, I can do time. Do you see a problem right now? Time. I need to get time into this problem, and it doesn't really seem like it. And that's because area is not a function of the radius. After 1 second, this was my area. After 2 seconds, this was my area. After 3 seconds, this was my area. Area is a function of time. Oh, by the way, isn't the radius changing every second?
Mm-hmm.
So the radius is also a function of time. That means I have to adjust this A of t equals pi r of t squared is the correct equation. The radius and the area are both functions of time. Time is the independent variable. Does that make sense? So what do I want? I want the rate of change of the area with respect to time. So what is dA dt? Think of this as thing. Want to be 2 pi r of t to the first power times what? I'm differentiating with respect to time. dr dt. There's no x in this problem. Time is my independent variable. And I have 2 different derivatives. By the way, would it be okay to just write this as 2 pi r dr dt? Would there be anything wrong with writing it that way? When you guys write y, how often do you write y of x? Like never? You know y is a function of x. So if I wrote this as just r, that's okay. The derivative of area with respect to time is 2 pi r, which by the way is dA dr, and that's dr dt. This is straight up chain rule.
it's a t, right? So it's pi parentheses r.
That's r of t, r of time.
Above that. That's a t, right?
Yes, r of t. So the rate of change of the area with the, yes, how many more times? R is a function of time. It's not a function of anything else.
I thought it was a -1 or so. I couldn't tell by your handwriting. That's all I was asking.
But I'm also saying it as I'm doing it.
Oh, okay, thanks.
Yeah, multiple times. So I have a function here, or I should say I have a derivative here, but I have 2 different derivatives in the same problem. Now, one of the easiest ways to interpret a derivative is to think units. Remember first time we started talking about the derivative. If I said consider the horizontal time, consider the vertical distance, Now you have a curve that says, here's how far I am from home after a given time. And then when you found the slope of a secant line, that was your average distance per time, so that's called your average speed. The instantaneous rate would be your instantaneous speed. That's how fast you were going right then. But you always had a quotient of units. What makes it really easy with derivatives is the units. This is area per time. Those are the units. This would be length per time. And that's length. So this is a scalar times length per time. That's now length squared, or area per time. So the units match. So I have two completely different rates in this problem that are related by this equation right here. This topic is called related rates. Now we talked about rates a little over a week ago when we started talking about derivatives. Anytime you had a graph in the XY world, in algebra we always do things without units. It's a bad habit, but we want you to understand the math first. In physics, in chemistry, in sciences in general, you always have units. And I mentioned that in actuality, your x and y axes would always have units. So the most common one would be time and distance, for example. So that means that whenever you found slope, slope had a rate. The vertical units over the horizontal units. So in this case here, a derivative always has units. Again, area per time, length per time, and they're related in this way. So we're going to embark now on some of these types of problems. They're actually pretty cool and they're pretty easy to solve. So a related rate means I am given two different units that produce derivatives. I have to know one of them. I have to know one of them in order to find the other. It doesn't matter, meaning I have to give you dA dt in order for you to find dr dt, or I have to give you dr dt in order for you to find dA dt. I don't need to give you both of them. I just need to give you one of them. So in this problem here, how did I start by saying? I said your radius was growing at a rate of 1 inch per second. Isn't that how we started? So the radius grows 1 inch per second. Isn't that a rate?
That's dr dt.
And that's, oh, awesome. That is dr dt. I'm giving you exactly the instantaneous rate of growth, which, by the way, the radius is growing at a constant rate. Do we agree that the area is not?
No.
No. So how fast is the area growing? Well, how big is the radius? When the radius is small, the area is not growing very big. But when the radius is huge, you're way out in the middle of the lake. Your radius is now, 1,000 inches. When you square 1,000 inches, you get 1,000,000. But when you square 1,001 inches, you're way more than 1,000,000. When my radius is huge, my area is growing fast. When my radius is small, the area is only growing by a little bit at a time. So I want to find, here's the question. I want you to find how fast the area is growing when the radius, let's say, is, 20 inches. Whoops, sorry, 20 inches. So I dropped the pebble into the water, and it's growing an inch every second. So literally, I'm saying 20 seconds in, how fast is the area growing? I want the instantaneous rate of change. I don't want an average. I want to know exactly at that moment in time. I'm giving you this value. I'm giving you this value. That value is constant. So can you tell me that value?
80.
Yeah, so let's do it. So here's what I'm asking. For this problem right here, I want to find the rate of change of the area with respect to time when.
The radius is 20.
Or it's the same, or the time is, are they the same thing?
Yes.
In this case? Yes. So I'm going to say evaluate it at t equal 20, and that will be, or r equal 20, same thing in this case. I'll put them both down. So it's going to be 2 times pi times 20 times 1. Because in this case, I said it was 1. It's not always going to be 1. So that would be, I think you said 80, that would be 40, right?
40, yeah.
40 pi what? What are the units?
Inches per second.
Inches
Squared.
squared.
Per second.
Huh. And It's gonna be, as I wait longer, that number's gonna grow. If I had done it sooner, that number would have been smaller. Okay? This is what related rates refer to. I have two different rates going at the same time. Usually, most problems, it's time. You're gonna do things with respect to time. So here's what you always have to start with. You have to start with some equation that relates your things in the first place. Like, area is pi r squared is how we started this one. There's always gotta be some sort of thing going on that you already know, that you don't have to figure out. Then I'm gonna differentiate, okay? So far so good? Let's try another one. Okay. All right, so have you guys ever seen libraries where they have the shelves go really high up in the air and they'll have a huge ladder? And it'll often be, there'll be like a rail or a groove in the ground.
Yeah.
So you can slide the ladder, safely sideways. You guys know what I'm talking about? And I can reach higher points than others. So I've got a situation where I've got a ladder, and the ladder is the fixed length. The ladder's length is not changing. I've got a ladder and it's leaning against the wall, and let's say the ladder is 17 feet. Okay? The ladder can start vertical, and I'm going to start moving it away from the wall. I could have the ladder start flat, and I'm starting to move it towards the wall, however you want to look at it. What I'm going to do is I'm going to take the ladder, and I'm going to start moving it away from the wall. But I'm going to move it at a constant rate, because I don't want it to get away from me. Okay? So the length of the ladder does not change, does it? So what I'm going to do is start moving it at a constant rate away. And I'd like to know, how fast is the top of the ladder moving? Is the top of the ladder going to move at the same rate as the bottom of the ladder?
No.
No, it can only do that if the length of the ladder changed. that one's going to kind of be weird at first, and you'll see. Now the top and the bottom are completely different. So let's say the base of the ladder moves away from the wall keep it real simple. Let's say at 2 feet per second. How fast is the top of the ladder moving when the base, let's say, is 8 feet away? So if it helps you, think of the ladder starting vertical. And I'm going to be moving the base away 2 feet per second, every second, literally until it hits the ground. At some point, well, probably 4 seconds in, at some point my base is 8 feet away. Right at that moment in time, how fast is the top moving? Now, is the top speed going to be positive or negative? Negative. If the base is moving away from the wall, the top is dropping, isn't it? Mm-hmm. So the top should be negative because it's going downwards as opposed to going upwards. If I was moving towards the wall, that means that my distance to the wall is decreasing, so then the top would be going up, wouldn't it? So the base and the top have to be, first of all, moving in opposite directions. Agreed? Because if they weren't, then we have a problem. Now, do we have an equation that relates everything? Well, let's throw in some variables. I don't know. How about we call the length of the base? How about x? Any good ideas for the vertical part?
Y.
Okay, good. Probably a good start. I could have used any letters of the alphabet. That probably makes the most sense. Is there an equation relating these guys?
X squared plus y squared equals 17.
X squared plus y squared equals
17.
17 squared.
Oh, great.
Do you all agree that that is a true statement?
Yes.
That's absolutely true. Now, I'm telling you the base of the ladder, the distance from the base, the x is changing at a rate of 2 feet per second. So the rate of change of x with respect to time, what would that be?
dx over dt.
That would be dx dt. Given dx dt is 2 feet per second, what am I asking you to find? dy dt. Since that's what I called my two variables. I called x the distance the base is away, and I called y the vertical. The base is moving 2 feet per second, so the rate of change of the base with respect to time, that's what dx dt would be. I'm giving you that as a constant, which is pretty common, by the way. Okay? I'm asking you to find dy dt. Well, how am I going to do that? By differentiating both sides of this equation with respect to what variable? T. Ooh.
And ladder starting vertical.
Yeah, think of, if it helps, think the ladder starting vertical, and it's going like this, so basically 4 seconds in. That's an easy way of thinking about it. So I want to differentiate both sides with respect to t, because that's the only way I'm going to get dx dt and dy dt. So x and y are not functions of each other. They're both functions of time because the ladder is moving. Okay? So if I differentiate both sides of this equation with respect to t, then that's a straight up chain rule. Without writing it, aren't I telling you this is really x of t squared plus y of t squared? Isn't that what I'm saying?
Yeah.
Because I'm saying x and y are not constants, they're changing with respect to time. So if I differentiate both sides with respect to t, then I'll have 2x times its derivative with respect to time plus 2y times its derivative with respect to time equals the derivative of 17 squared,
0.
which is 0. Good. I like that one. I'm telling you that you know dx dt. I'm asking you to tell me dy dt. Can I get that by itself? The dy dt?
Yes.
Yeah. Throw that guy over there.
You can divide both sides by 2, right? First.
Yeah, so how about I write dy dt equals negative 2 dx dt over 2y. Now I can cancel the 2's, obviously. X and y are not constants. They are distances that are changing. But dx dt is a constant because I said it's moving exactly 2 feet per second. That's not changing. Okay? I asked you then, this is in general, I want a very specific one.
And 8 feet away. So.
I want dy dt evaluated for what value?
X equals 8.
When x equals 8. So I'll write it, the formal notation, x equals 8. Well, that's easy enough. That's going to be negative 8 times 2 over, oh, how am I supposed to figure out what y is? Wait a minute. How in the world would I ever be able to figure out y on a right triangle where x is 8 and the hypotenuse is 17?
Plug in x is 8 in the original function.
Did everybody figure out how to figure out the y value?
Y squared equals 17 squared minus 8 squared.
Yeah, so therefore y is, what's y? Notice I give you a happy number.
15.
15, exactly. Okay. So I'm asking you, what is the y value at the moment that x is 8? It's Poe. I haven't heard from Poe all day today. Wow. Okay. Is y always going to be 15?
No.
No, it's only going to be 15 when x is 8. What if x is bigger than 8, then y is smaller than 15? So in this problem here, when x is 8, you said y is 15. Here's my answer. What is it?
Negative 16 over 15.
And the units? There are definitely units.
Feet squared over second. Oh,
Just feet per second.
yeah. All right.
Am I moving downwards at the same rate I'm moving horizontally? No, moving horizontally at positive 2. I'm moving down at this moment of time just a little more than 1 foot per second. Now, here's what's interesting. As x gets bigger, what's happening to dy dt? Just for fun, get out your calculators. Let's put an x value that's bigger. I mean, how big can x, what's the biggest x could possibly be, by the way?
17.
17, yeah, x can't be bigger than 17. My ladder's not growing. So just for fun, put in 16.9. So if x squared plus y squared equals 17 squared, then you're right, y squared is 17 squared minus x squared. I want to use exactly the same problem we just did, but instead of 8 feet away,
Y,
I went almost all the way to the bottom. I
Y,
want x to be 16.9.
Y is equal to 1.84 hundred.
Well, so what's y squared equal to? Start with
Oh,
that.
well,
Make it easy.
3.39.
So you don't want to just use the square root, right? So 17 squared minus 16.9 squared is 3.39, so that means that y equals the square root of 3.39. I have a calculator, I don't need a budget. So let's change this. Does that change my answer, by the way? Before you put it in, am I moving faster or slower? Then we just got negative 16/5. Am I moving faster or slower? Am I dropping faster or slower, do you think? Is the ladder speeding up or slowing down as it goes towards the ground? Why would it be speeding up? Well, you say, yeah, gravity. My denominator's getting really small, isn't it?
It's approaching 0.
Hold that thought. You are definitely on the right track. So what is this speed now? This is about approximately 18.3 something. Wait, negative. Just a moment ago it was barely 1. It was moving at 1 foot per second. Now it's moving at more than 18 feet per second. Okay, just for fun, because again, that is our primary goal. Let's get a little bit closer. I'm almost to the ground. You're gonna, this is so cool and so weird at the same time. This is a natural phenomenon. And I know, I know somebody made this mistake and they paid for it. Okay, now it's 3399 under the root. I'm sorry, it's 0.3399. Okay, so everything's exactly the same except I'm now using 16.99. I can't use 17 because y would be 0, wouldn't it? I can't have a 0 in my denominator. But I'm approaching 0. So negative 16.99 times 2 over the square root of 0.3399. What does that give us? It's kind of crazy math. You get about what? Guys all have calculators. What do you get now? About what? Don't dare answer, you want to be wrong. And I was telling one of my other classes, this is the only class I know when I ask for calculation, everyone does this. If I don't move, you won't see me. And I'm kind of expecting everybody can do this because this is not math, this is arithmetic. You're putting numbers in a calculator, but you gotta know what the numbers are and what they mean when I'm done. Anybody got a number yet? By the way, I don't provide any calculators for this course, so if you don't own a calculator, you might want to acquire one at some point. We will use them on occasion. Not often, but on occasion. So you got a number?
60.67
That's close.
I got negative 50.
or negative.
Negative 58.
Point
Oh.
3.
Yeah.
Is this getting faster?
Yeah.
60 feet per second is pretty fast. If somebody threw a ball at you and hit you, that would hurt. That's really fast. The closer I get to the ground, what's happening? The ladder's speeding up. In fact, as x is getting closer to 17, isn't y getting closer to 0?
Yeah.
So what's happening to this quotient? It is starting to grow really without bound.
Limits.
Literally, it's approaching infinity, believe it or not. Now, I knew somebody did this. I said, when the ladder is falling, should you ride it all the way to the ground or should you jump off? First of all, I don't think you could ride it all the way to the ground. It would actually. I'm pulling the ladder away at 2 feet per second. There's a point, we've already passed it, where the top of the ladder is dropping much faster than gravity would suggest. You understand? Gravity, it would drop at a different rate. As I'm pulling it away, the top is speeding up. It's going way faster than if I just dropped an object. It's going much, much faster than that. If I hang on to the ladder for dear life as it's falling, it's going to be more like an airplane crash. I'm going so fast at the moment of impact that things won't do well. So if you even could hang on to the ladder, what should you do as it's falling? Jump off. Don't ride the ladder all the way to the ground because it's speeding up. If I did 16.999 and we keep going, that number there is getting into, your supersonic jet pretty soon. So no, is it really that fast? If I'm moving it away at a constant rate, yes. Because the top is falling faster and faster, which is weird because our first inclination is to think the top is moving at the same as the bottom. But it can't be. Think about it this way. This is 17 when this is 0. Right now it's 8 and 15. Those don't add up to 17, do they? This length and this length are never going to add up to the hypotenuse. That's not how it works. Oh, so if this is increasing at a constant rate, this can't be. Otherwise, every time this moves 2 feet, this would drop exactly 2 feet, and I'm maintaining. That's not how it works. It's the sum of the squares that stays constant, not the sum of the x and y. So that one's kind of crazy, isn't it? That kind of defies common sense at first, but it is a really cool thing. Now, some of you may have been asked questions of this nature before. We're standing at an intersection, and you decide to go north, and I'm going to go east. We're walking away from each other. If we're both moving at a constant rate, we have the same stride, then the distance between us is growing. Agreed?
Yes.
But is it necessarily growing at a constant rate?
No.
No, for the same reason. No, it would be growing faster than a constant rate. Isn't that interesting? Now, one of my kids just came home for the weekend and we got out the blow-up mattress. And I always love using blow-up mattresses. This is our next thing here. When you're blowing things up, everything seems a little bit stranger. How many have ever had to blow up a mattress with your mouth? God, that's the worst thing ever, especially as you get late in the process and you start getting dizzy and your head's about to explode and all that. How many have ever blown up a whole bunch of balloons? Like your kid's party blown up. Yeah, it's awful. But the one thing about a balloon, I'll use a balloon. You blow a balloon, it's like a I'm blowing in the same amount of breath each time, but the expansion seems like it's getting smaller and smaller and smaller. At first, the expansion is huge, isn't it? I noticed right away. Maybe I'm using the automatic, the air thing. And at first, it gets really big, and then the longer I do it, it seems less and less and less and less. You're blowing up the air mattress with your mouth. It might seem like it took you a few minutes, but you got a lot of air in, but the longer you blow it, it seems like it's hardly doing anything. So what we're going to do is we're going to have the first inflatable classroom. We're going to do that next week. It's going to be a perfect, make it simple, just make it a perfect cube, the shape of our classroom, but it's going to be completely deflated. So each of you is going to get turns blowing it up. Okay, so what we're going to do is all of us are going to train ourselves to blow air at a constant rate because we don't want to hyperventilate, So we'll just pick a nice smooth amount and we're going to blow that at a constant rate. So we're going to fill this thing eventually. Now, when I'm blowing up, just like with the balloon, if I'm putting air in at a constant rate, then the volume is changing at a constant rate. Is the radius of the balloon changing at a constant rate?
No.
Or did we just agree it's really big at first and it slows down? You follow me? The rate of change of the radius and the rate of change of the volume are completely unrelated. In fact, an easy way to think about it, volume involves the cube of the radius. Oh, they can't change at the same rate. If the radius changes at a constant rate, then the volume would be getting really huge, really fast, like our example with the with the rings. So we're gonna blow up a cube. We have an inflatable cube. Now, let's suppose that whether you're doing it by mouth or you're doing it with a, an air hose or something. So you're going to inflate or make it simple, you have a balloon in the shape of a cube. And we're gonna blow it up so big that it's gonna be as big as the classroom. How's that? We're going to inflate a cube at a rate of, let's see, what would be a lot of air? A liter per second is way too much. Probably, let's say, this is not a lot. 200 cubic centimeters. That'd be a fifth of a liter. That's not a lot of air. You're not gonna die. Okay? So you're gonna inflate a cube at that rate. Okay? When the edge is, let's say, 100 centimeters, how fast is the edge growing? I'll show you what that looks like pictorially. I'm using a nice happy round number there. When the edge is 200 centimeters, how fast is it growing? Okay, actually I'm gonna change one thing. I'm gonna make that 300. I want this to be simpler, numerically. Okay. So you've got a cube. In Calc 1 and Calc 2, strangely enough, the only geometric shapes we really ever use are squares, cubes, circles, and spheres. Those are the only ones we ever use, because they're the only geometric shapes in 2 and 3 dimensions that have only one variable. Right? The circle and the sphere has only the radius, the square and the cube have only the length of the edge. We can't do other shapes right now because that requires more than one independent variable. So, what do you want to call this? Just call it X? Let's call that X. Now, one of the problems of ambiguity when it comes to the geometry is people say, well, why don't we just call that the side? Let's pretend this is a cube. Don't you call this the side? But in 2 dimensions, if I'm looking at this as being a square, I call that length a side. Side is an edge in 2 dimensions, side is a face in 3 dimensions, so we never use the word side because you couldn't know, do I mean the 2-dimensional or the 1-dimensional? So we say the edge, then what do I call this whole plane here? It's called the face. Yeah. We talk about the face of a building, you know exactly what we're referring to. Oh, okay, that seems like an odd word, but therefore there's no ambiguity. So I want the edge. So what is the volume of this thing? It's a cube.
X cubed.
X cubed. Okay? I have to determine what am I given and what am I looking for. That is not automatic always. I said I'm inflating a cube 300 cubic centimeters per second. Is that a volume or a length? Cubic centimeters.
Volume.
That's a volume. So I'm giving you the rate of change
The
of
dV/dt.
volume with respect to time. I'm giving you dV/dt. Everybody see that? How do you know? Simply from the units. So I'm given the rate of change of volume with respect to time is 300 cubic centimeters per second. I want to find the rate of change of the edge with respect to time, which would be dx dt, but very specifically when? When x is 100.
100.
Does that make sense? The statement of the problem, this is what you can infer from it, and that's, you have almost everything you need. There is one more piece of information you absolutely have to know, and that would be the volume. If you didn't know that, I would tell you. But the volume of a cube is not complicated. And the shapes, like I said, we tend to use our circles, spheres, squares, and cubes because they're the easiest ones. Okay? So how am I supposed to do this? I need to differentiate that equation with respect to time. And that's what the chain rule tells me. Volume is not a function of x. Volume is a function of x, which is a function of time, ultimately. Okay, so let's... Also, here's my... What is dv dt? You don't need to rewrite this. This is volume as a function of time. This is x as a function of time cubed. So what's the derivative of x as a function of time cubed? 3x squared times the derivative of x with respect to time.
dx dt.
Beautiful. You see it? Do I have everything I need in this problem pretty much to finish this now?
Yes.
Yeah, I have every single piece of information, but don't put numbers in and then start solving for things. That's inefficient. Solve for the thing you need, then put the numbers in. I'm given this, I'm asked for this. So the first move you really want to do is say, okay, dx dt is what?
dv dt divided by 3.
Oops, sorry. dv dt. Sorry.
Divided by 3x squared.
Okay, now stop for a moment. This would be true no matter what dv dt was. This would be true no matter what value of x I gave you. This is the relationship. This is true for any situation. I want the very specific situation where x is 100. So now I'll say, what is dx dt when x is 100? Now that means I can replace x with 100. You can't replace x with 100 for all cubes, only this part. So what was our numerator?
300.
300. Our denominator is 3 times 100 squared. What's this? And therefore, what is our answer? Use your calculator if you have to.
110.
Third.
1/10?
1/3.
1/3.
Oh.
100 squared.
Use your calculator.
1/30. Oh yeah, 1/30.
I'll make it easier on you. 3 times 100 times 100. How about 1 over 100? Units? Centimeters per second. Would you say this is a large change or a really small change? Really small. Would the naked eye see 1/100th of a centimeter per second change? Do you think it'd take you a while? So what's happening is you have the cube balloon. I don't know if those actually exist, but you know they're balloon animals. There's got to be cube balloons, right? Balloon cubes. So you start and it's blowing up and you're blowing at a constant rate and it's going slower and slower and slower. I'm adding air, but I'm changing in all 3 dimensions. That's why it's so slow. By the time it's 100 centimeters across, it's only increasing 1/100th of a centimeter per second. But it's still growing. It's never going to stop growing. What if I had said, okay, what about when it's 200 centimeters across? It would be even way smaller than that, wouldn't it? The bigger the cube, the less change I see. That's really what it comes down to. This would be true for anything. Now, I said I was inflating it. See, this is the situation I have at my house. You've got the humongous air mattress that's been inflated. Now I want to deflate it. So what if I deflated this? It's already completely blown up, and now I'm going to deflate it at a constant rate. And I'm going to deflate it at exactly the same rate. It's huge. It's as big as the classroom. I'm deflating it. At some point, it's going to be only 100 centimeters across. How fast is the radius changing on the deflation? Anybody want to guess?
Negative.
The negative of that. Yeah. Because what's the only difference in the problem?
The direction.
This would be negative if I was deflating it. You agree? Oh, okay. That makes perfect sense, I hope. So deflating, it's getting smaller, and so my rate of, if the rate of change is negative for anything, it means that thing's getting smaller. If the rate of change is positive, it's getting bigger. What if the rate of change was 0?
It's not changing.
Then it's not changing. And that's probably not a good answer in this case because things are changing. Okay? So far so good? Questions? This is kind of an interesting concept. Is the math complicated? No. You're taking one derivative, but it's what am I doing with that thing? What's different is it feels like we have so many variables. Well, what I have is one equation, but the one thing that is changing is time, which I don't see in the equation. And that's why I have to see it. Oh, volume really is a function of time. Okay? So I'm going to write this a different way, because this is still chain rule. V is a function of x, right, which is a function of time. dv dt is 3x squared dx dt. But if I said, what's the derivative of v with respect to x, isn't that 3x squared? Isn't the derivative of this just 3x squared? I want you to notice this. This is the chain rule. dv dt is dv dx, dx dt. This is a quantity, this is not a quotient. But from a notation standpoint, it kind of gives the illusion that things would cancel, wouldn't it? From a notation standpoint. If I'm doing my chain rule correctly, that's what it should always look like. Differentiating with respect, this was the outer door, and now I got to the inner door, and so on. Now, here's why I've said you don't use prime notation. For those who use prime notation, this is v prime. For those who use prime notation, so is this. You have a v prime of t and a v prime of x in the problem, so that's why you don't use v prime. Would it be okay to write v prime of t and v prime of x and x prime of t? Would that be okay?
Yeah.
Sure. Yeah, you're not saving any time, but yeah, that's exactly the same thing. We use f prime of x when it's function notation. We use dy dx when I'm given y is, but they mean the same thing, as long as I understand that. But this is really important to recognize from this is the chain rule, exactly. And so I had to do that. This is the chain rule factor. Okay? So far so good? It's kind of wild, isn't it? So we just did that one. Let's do another one. Let's do a similar one. All right. You're going to let the air out of a spherical balloon. One or two? Okay.
Two.
Okay, good. At a rate of, you're in a hurry. I mean, you're gonna sit on the balloon if you have to, right? You want to move on. You got to get out faster. So let's just say we're going to do it at 1,000 cubic centimeters per second. That's a liter per second, right? How fast is the radius changing? This is a huge one, but this is like, we could all fit it. James and the Giant Peach, kind of big. You guys know how big that is, right? Yeah. Yeah, we could all live in it with the 6-foot ladybug, which to this day that still scares me, that concept. But James and the Giant Peach was important story when you're growing up. How fast is when the radius is, how about 200 centimeters? So this thing was huge, and you're getting rid of a liter per second, which doesn't seem like a lot. So what do I notice much change at first? It's huge. I'm losing a liter per second. You could think of it as leaking out. Do you see a huge change? No, but after a while, as it's finally getting smaller, that 1 liter is taking up a larger percentage of the overall volume, isn't it? Because the overall volume might only be 10 or 20 liters. Oh, and at some point, I'm down to 2 liters, then I'm down to 1 liter, then I'm down to 0 liters. So at the end, would you see it going really fast? Yeah. So you'd see it speeding up in terms of the size change. So, tell me about my answers. Are they positive or negative? Negative because I'm deflating, so I'm decreasing. Will that show up in the problem? Yeah, because I'm going to use a negative number here. Now, what is the volume of a sphere? spheres. Do you remember this one? It's a good one.
4/3 pi cubed.
4/3
Pi r cubed.
pi r cubed. It is implied by the question that both the volume and the radius are functions of time. And it is absolutely correct to write v of t and r of t. But you can also be lazy. Right? Everything you're doing with x and y, nobody writes y of x, it's implied. So as long as you realize that v and r are functions of time. Why is that important? Because when I differentiate, that's going to dictate what the derivative looks like. So I want to differentiate both sides with respect to t. So here's exactly what I'm going to do. I'm going to go d dt, d dt. That's what's absolutely taking place here. Now when I do that, the left side clearly is just dv dt. So what's the right side?
4 pi r squared.
And it's implied that's r of t, and now I need to differentiate that, and that gives me
dr dt.
dr dt. I have two different rates in this problem. It is not possible for me to continue unless I was given one of these rates. Was I given one of these rates?
Yes.
Which one?
dv dt.
How do you know? You're right, but how do you know?
Because of the units of,
Because of the units.
yeah.
That's really all it comes down to. Now I'm going to do this one a little different than the last one. Do you notice that I did the problem unitless, but I put the units in the answer? If you're in a physics class, they probably want you to put the units in at every step of the way. I'm not a big fan of that because it looks very cluttered. It becomes really hard to read, but the most common error in this problem is not the wrong numerical answer. No, the most common error is the wrong units. And if you're in a physics class, they'd say that's the most important part of the problem, is the units part. So when I'm doing this, I'm looking for dr dt, correct? So dr dt is equal to dv dt over 4 pi r squared. I want dr dt when? At the moment the radius is 200, and you notice these are separate statements. This is a derivative, this is a formula, this is not a scalar. Because if the right side was a scalar, then you're saying dr dt is a scalar always. You're always going to get the same answer. Well, you're not. You're only going to get one answer per, each radius you choose. So when I do this, what is my numerator? What was the given?
1,000.
Almost. Starts with an N.
Negative.
Negative 1,000, yes. Negative 1,000 what?
cm cubed.
Centimeters cubed per second. I'm going to put the units in this time. In the denominator, 4 pi is a scalar. It's not, it doesn't have units. It's just, the coefficient. R is what?
200.
Good time.
200 centimeters, and now I'm going to square that value. Well, I should get some canceling.
The 1,000 that you read, that's like,
But that's a 200 squared, so careful. There was definitely canceling, but I'm squaring the 200.
well, that's only 4,000, that's not that much.
40,000.
So that's 40,000, now it's 16,000, so 116?
Yep, negative 160.
160.
So far so good? Now, what are the units of my answer?
You forgot a zero.
Did I lose a zero?
It's 1 over 160.
40, what did I, oh, 160, thank you, it's 160, good catch. Does it have units?
Yeah.
Centimeters per second.
Centimeters cubed per second divided by centimeters squared, is that centimeters per second?
Yes.
Yeah.
Yes. If you're in a science class, they probably want you to do this. And now you know that you got this right. I don't care if you put the units here. I find it sometimes makes it harder to read because there's just too much stuff. But that wasn't that bad. Do you agree? So I can certainly put the units here. I just got to make sure I put them in the answer. Is that big or is that small? That's pretty small. It's pretty small, and it is negatives decreasing because 200 centimeters is still a pretty big sphere. What if we got down to really small? Let's say instead of 200 centimeters, we were only at 20 centimeters. Well, if we were only at 20 centimeters, this answer would be 100 times bigger. Because I'm factoring out a 10 squared in the denominator. Oh, so my rate of change would be 100 times faster if I was 1/10 as big. Okay, so this is what related rates are. Related rates, again, probably time. That's the most common thing. I have things that are changing, different things that are changing with respect to time, and the things that are changing are not the same units, but they are related by some form of an equation. So we use the ladder, we use the Pythagorean relationship. Okay, in this case, we just simply use the volume of a sphere, and so on. So we could do this for any problem where we have two things that are changing at the same time. Now, in the case of the ladder, both things really did have the same units, right? They were both distance per time. So that one actually was probably a little less challenging from that standpoint. But this is the first application. It's far from the last application. It's the first one because it's the first one that we can now do based on what we know. Now we build up. On Wednesday, we are going to round out the material that the first exam covers, and we're going to look at exponential logarithmic functions. Logarithmic functions, you could argue, are probably the most important functions you look at in calculus. More important than polynomials because of their uses. Did anyone here start off in the business calc route and then you change to regular calc? That's actually not that uncommon. People start off in business calc and realize they're in the wrong one because they wanted to go engineering and that one doesn't count. So you end up here. Logarithms are just about the only thing they do study. But logarithms make everybody uncomfortable because we don't all know, the algebra really, really well. So we're going to review some of the algebra and the things about logarithms because we're going to start the calculus of exponential logarithm. Okay, let's go ahead and stop that.